John, welcome back.
Hi Neil, how are you doing?
Doing great, thank you. We've had a very, very busy but exciting day. Lots of wonderful presentations, and I know everybody's looking forward to hearing from you. So let me.
Oh yeah, I realized I gotta share my screen. I that
I just made you a co-host.
okay, I got it. There we go.
So whilst you're doing that, let me introduce you a little bit for people that don't know you. I'm going to read a little bit about your bio, and actually, I've been learning a little bit by reading your bio as well, so that's always fun. So John is originally from Towson, Maryland, is it, which is near Baltimore, where
Yeah,
his parents were psychiatry residents. But you moved to San Antonio when you were pretty young, when you were 6 years old. So this has been home for quite a while, where your parents practiced again after he left the army. You're the middle of five children with two brothers and two sisters, so you're obviously the peacemaker as the middle child, right? So that's kind
pretty
of the role
much.
the role they tend to play. I know that because I'm a middle child as well. As a child, you wanted to be an architect, but when you grew up, you spent most of your time programming basic on computers. But you attended UT Austin, majoring in physics and philosophy. Now that's a kind of like two opposite ends of the spectrum there, but I suppose they come together very well. Then you went to UT Health San Antonio Medical School, and then, because you didn't have enough to do, you then completed your PhD in biostatistics at the University of North Carolina, Chapel Hill. So, kind of, you've been a very busy guy. I've got here that your professional interests and expertise lie in clinical trials, aging and genomics, and of course the chromosome 18 condition. You're married to Shell, who is a pharmacist and professor at the Carnot Word University Feek School of Pharmacy, and you have two children, Alexandra, age 10, and Isaac, age 14. And in your spare time, you like to read, run, and argue about who makes the best pizza.
Yeah.
So, as pizza experts from a brief stint in Chicago, who still brings handmade pizza back from Chicago. I can't wait to sometime perhaps try some of your pizza. So awesome. Well,
Thank,
I
thank you.
we're looking forward to hearing from you. It looks like your presentation is up and running.
You see
So
it?
I will pass it over to you.
Okay. Can you hear me?
Absolutely.
All right. Thanks for the intro, Neil. Some of those details I even forgot myself, so it was good to refresh
It's
to
it's
relive
all
those.
it's always funny hearing your own bio, isn't it?
I know. It's like, oh my goodness, did I do that? I guess I did. But yeah, so I don't really need. Yeah, I was prepared to like give the brief intro of myself, but thanks, Neil. That was really a good intro, and I'll just dive right into our research update for 2024. And some of this, if you went to the conference in Charlotte this year, you might have heard, and I have some updates on top of that because everything these days changes so quickly. And but just to give a quick overview, what's our next opportunity going to look like, given that there's so many possibilities. And so we try to answer that question strategically, driven by our goals and the funding opportunities provided by the sponsors like the National Institutes of Health and others. And to get these grants, we need to have research plans that are believable, that are seen as feasible by the grant reviewers, and we need to align our research goals with those of the sponsor. So each grant opportunity tends to fall in one of 4 stages of development, and sometimes we call these stages the translational pipeline. And each of these stages kind of interconnect and feed into each other, so that grant reviewers see it as very advantageous to have a research portfolio that's engaged with all 4 of these stages of clinical research development. And so the first stage, I'm not sure if you can see my cursor over here, but it's identifying basic research designs, and which we're looking at genes and treatment targets. Typically, we do this early stage in the laboratory and in animal models. And in that category, we have an R03 grant with collaborators who are developing organoids and looking at mice models of chromosome 18 Q minus. And then the next stage is early translation into humans, and which we're assessing risk factor, identifying potential treatments, and looking at our clinical outcomes. And there we have some funding in terms of an R03 grant that's in the Kids First research program. And then the next step is our clinical trial phase, when we're translating our treatments into patients. And we recently, in this October, had a submission to the NIH looking at myelination endpoints. And then the last of the 4 stages is translation into practice, where we're looking at how our patients are living in the community and the long-term treatment effects, and trying to identify new patterns of disease. And the first step is this basic science or laboratory research, in which we have an NIH grant. And there's the title. It's Molecular and Cellular Mechanisms of Chromosome 18q23 Dysmyelination. And it's a 2-year grant, and there are 2 collaborators, as well as Donna Lehman and Narobu Harori. And Donna is developing human brain organoids, looking at this dysmyelination process. And an organoid is a brain, a model brain grown in the laboratory that can be used to identify what the impacts of chromosome 18 genes are in the developing brain, specifically looking at myelin growth and development. And this dysmyelination term that we're using is a fancy word for a problem with the electrical wiring of the brain. And Dr. Narobu also, instead of working in the in vitro models, that is the dishes, he has mouse model that are shown here. And these are the mouse model brains, and showing the degree of dysmyelination. And we use these 2 models, like human brain organoids and mouse, in order to test treatments and identify gene mechanisms. And we know that, like, it's not one particular gene necessarily, but a couple of genes working in combination that cause the problem. And it would take a long time in order to identify this using human models. So these mouse and organoid models allow us to more quickly and less expensively screen and test compounds that may be improving myelination. And in our early human studies, we have a program, a grant, and sponsored by the Gabriella Miller Kids First program. And their aims are to uncover new insights into the biology of childhood cancer and structural birth defects. And even though our focus is not cancer, we share the objective in understanding the mechanism through which genes affect the risks of birth defects, and what type of birth defects are we more likely to get given specific genetic anomalies. And we often see birth defects in the heart, the brain, the kidneys, and the ears. And one of the models for this that Dr. Cody has developed is this idea of a critical region. And these critical regions are shown in this pictograph here with people with anomalies corresponding to regions having specific clinical risks like autism or psoriasis or seizures or even difficulty in hearing. And what the Gabriela Miller grant does is it allows us to do whole genome sequencing in which we can distinguish between two people who are missing the same region but are affected differently. And instead of just studying the positions of the deletions, we're identifying the precise sequence of the corresponding intact genome to understand why some people are resilient and the other people might be more susceptible to clinical conditions. And the stage that I'm working on now is this RO3, the clinical database enhancement, in which we're going through all the medical records of our GMFK participants to look at their genetics and their corresponding clinical conditions. And what we're doing is we're labeling all these clinical conditions with these HPO terms. That stands for Human Phenotype Ontology, which is the sort of a standardized code that we give particular structural birth defects or clinical conditions so that we can understand those in the larger context of medical research and compare our results with others to understand which genes are associated with which conditions. And a partner we have with that research, who's an expert in deep sequencing, is Santosh Girirajan from Penn State, and he has expertise in sequencing algorithms and identifying modifications in the DNA and linking these to specific clinical outcomes. And that's the next step is, of course, doing these chart reviews. And one of our clinical research associates, Brittany, has gone through the entire medical records for all 150 participants and identified the major systems with structural birth defects. And we're now about, I would say, halfway through coding all those birth defects, starting with the heart and then going to the brain and then the respiratory system, GI system, et cetera, and labeling all those so that we can compare them to the larger database that GMFK has developed. And our next step is this early clinical trial readiness submission. We submitted a grant with some partners here at UT Health San Antonio, in which we're preparing for clinical trials by precisely measuring dysmyelination using multiple techniques in order to see which treatments could potentially improve that. And why are we studying dysmyelination? Well, we want to develop a treatment that it can improve independence, and we want this to be believable by grants funders. And dysmyelination is something you can see inside of an MRI scan, which I'll show you in a little bit, and that is very convincing if you can make an impact on it. And this is a common chromosome 18 condition, and also dysmyelination is a major factor in different diseases such as MS or multiple sclerosis, Alzheimer's, autism, as well as a risk factor for seizures. And here is the critical region for dysmyelination that involves around 4 genes, not one particular gene, but it has to be in some combination that we're hoping to understand with our other basic science projects. But here's the scan of a person with 18q minus, and you can see a comparison scan with a typical MRI showing these dark tracks, which represents sort of the rich myelin that you see in a typical brain that's sort of absent or faded out in 18q minus. And our objective with this clinical trial grant we submitted is to have clinical trial endpoints that are measured objectively, not subjectively, through multiple means or channels. So we're going to measure the blood or urine biomarkers for myelin. In terms of the physiology or function, myelin affects the reaction time, so we're going to measure that as well. And we're going to, of course, examine this anatomical differences in myelination and look for behavioral differences, that is, in attention or memory. And these endpoints, although we don't have a treatment we're actively testing, we need to establish how well we can measure these endpoints and how the objective measures corresponds with real clinical impacts. And the fourth stage of research is studying how our patients and participants are living in their community, what their challenges are, what the long-term effects of their conditions are, and looking for new patterns of disease. And we're studying several dimensions of that, including in trisomy 18, FSHD, and seizure research. And one of our interests is aging. You know, what changes do we see as our chromosome 18 cohorts get older? And one of the adult onset conditions that we're studying now is called FSHD2, which involves a gene in chromosome 18p minus, and it occurs in about 1 in 8,000 people. And it's associated with sort of a general muscular weakness throughout the body and underdeveloped musculature, potential difficulty walking, and difficulty with facial expressions. And Doctors Karkar and Tawil, Karkar is in our clinical research team, and he'll talk to you later today. And Dr. Tawil is an expert in FSHD. We're getting videos, remotely collecting these of our participants to see who of those who are at risk, do any of our participants have signs of FSHD2, because it's potentially treatable and we can address those issues early. And in the adult onset conditions, we're considering, you know, what are the genes involved, what are the mechanisms, as well as what are the emerging symptoms or conditions that we're finding as our patients get older. Some of those involve dystonia, that's a muscular weakness or lack of tone, and then arthritis, you know, which is a symptom, but we might not necessarily know what's causing that right now. And those are in 18p minus individuals, and individuals who are 18q minus, what we're finding is that they are having a higher rates of hypothyroidism and autoimmune disorders relative to the age which they more typically onset in the normal population. And we're also finishing up research on trisomy 18 as well, and Janine kind of discussed some of this earlier in looking at those who lived longer than 1 year and what their cause of death was, and looking at ongoing issues in trisomy 18, and specifically what are the characteristics of the disease in terms of the subjective lived experience. And one of our research associates, Amukta, has used AI to identify themes that are challenges and characteristics of that condition. And Dr. Carey, trisomy 18 expert, is reviewing the last draft of that now. And also we're following up with a seizure survey after 10 years, and Dr. Karkar is leading that. And this survey is currently open, so we have about 200 responses, but even if you don't have seizures or history of seizures, we encourage everybody to complete that. Of course, if you don't have seizures, it'll be like a 2-minute survey. So that's a quick contribution you could make if you have a chance. We're continuing, of course, our annual surveys, looking at our medications that people are taking so that we can understand the rates of conditions and try to figure out what patterns of new medication use and new conditions are emerging over time. And we recently completed adult living assessments, examining living arrangements, educational attainment, and work status of the different chromosome 18 conditions. And I'll go through that quickly. And these are adult conditions. So we're looking at people who are over 18 years old. And so distal 18q minus deletions without the TCF4 gene, we had 54 responses, and of those, 3 were married and 1 with children. And the living arrangements are shown here. A slim majority live with parents. And here's the educational status. The majority have a high school diploma or above. And the work positions are shown here with 2/3 working and either part-time or a day habilitation program, volunteering, etc. And then we have distal 18q minus deletions with the TCF4 gene, which is a more dysfunctional state. And we had 8 responses, none married and none with children, and about half of those with a high school certificate or above. The majority of those not working. And then proximal 18q minus deletions, we only had 3 responses, none married, none with children, and all 3 had high school certificate or equivalent or above. And the different living arrangements are shown here, sort of a mixture. And chromosome 18p minus or p-arm deletion, we had 44 responses, 1 married, none with children, and about 3/4 living with parents or guardians. And the majority of those also with high school diploma or above. And their work positions are 2/3 working, 1/3 not. And of those 2/3 that are working, there's part-time, volunteering, and day habilitation program. And here are trisomy 18Ps. We had 11 responses, 1 married, 1 with children. And about 2/3 living with parents or guardians. And trisomy 18p also had majority with high school certificate. And here are the trisomy 18 work positions. Majority not working, but 25% part-time paid, 8% either volunteering or 8% in a day habilitation program. And tetrasomy 18p, we had 30 responses, none married, none with children. And about 80% living with parents or guardians. And the highest education levels shown here, again, about 50%, more than 50% with high school certificate or above. And the work positions are shown here, about 1/3 in a day habilitation program, 40%. Currently not working, 13% volunteering, 8% part-time paid positions. And then ring 18, we had 11 responses, none married, 1 with children, and about half living with parents or guardians, about 1/3 independent supported living, 18%, parents independent department. And the educational levels, about high school certificate or above for most. And here are the work positions for ring 18 participants, about 35% not working, 29% in day habilitation, 18% part-time paid. Okay, and here are our resources. We have the registry website, and the clinical management guidelines are shown here, and they're available at the our website. And one of our new developments, we recently got a small grant to develop an app that we have a screenshot here. And this web application identifies the clinical risks associated with specific anomalies. A lot of times people can have a genetic report that shows that a particular region is deleted or amplified, and we're not sure how to interpret that report. And this tool allows someone to enter a specific anomaly, and based on Dr. Cody's gene dosage map, this app will return or make a little mini report of the genes that are clinically impactful in the affected region. And this allows us to report the significant genes, as well as what are the likely clinical impacts of those. And in this screenshot, we're showing the genes that are in this region. This is sort of the highlighted region here that could be deleted, shows the significant genes, the clinically relevant genes, and it shows the penetrance or the risk of the condition. It shows the list the variation, a lot of unknowns here, but it shows the variation and how large an impact that gene can have. And it also lists the strength of evidence. Sometimes we're sure that a gene caused something. Sometimes we're maybe sure or suggestive that a gene's caused something. And then it tells the specific clinical effects of those genes. And the idea is to get some kind of customized risk profile based on the genetic report that someone may have. And after we've kind of got a little more development in, we'll be looking for volunteers to try it out and to get some feedback on whether this provides helpful information and how we can improve the application. All right, and that's the end, and I'm happy to take any questions you may have.
Well, Jon, well, thank you so much for that. And that is an amazing amount of data. When do you ever sleep?
Well, it's a big team, and I have to say, it's sharing the load with Dr. Cody and the rest of the research team, Brittany, Amukta, and Catherine. So yeah, we do get some sleep. It's true, and we want to help. Also thank Dr. Karkar, and it takes a lot of collaborations to keep this going. So we thank you for any support you may provide, and also thankful for our collaborators. We get new collaborators every day. I don't know if you know this, but Brittany's sister found a new collaborator at University of Pennsylvania. So we're really excited about that, looking at, I believe, trisomy 18. So that's really, it's an expanding load, but we're finding new partners to help us support it. So that's the fun part.
That's amazing. And thank you. I mean, I know I've got some questions, but we've already got questions coming in. So I'm going to ask the first one. You mentioned FHD2, I'm sorry, FSHD2 being treatable.
That's right.
How do you treat it? And that I know that's probably a big question.
Yeah, I think probably there's unfortunately not, I think, a physical therapy. It's probably supportive therapy, but yeah, probably like an occupational type therapy. But they do have FSHD's to Society that helps with finding treatments, and um, it is yeah, not I shouldn't, I probably overstated if I said it's treated. It's not curable, unfortunately, but
It's
there are
manageable.
therapies.
Okay. Well, and is that organization, do you know, the FSHD2, is that in the US if people kind of search that?
Yeah, I'll look for that. I'm not sure where they're based actually.
Okay. Well, we can do a little bit of research on that whilst we're talking as well, and we can always share that with people. Another question that's come in is that it says, how do you take the seizure survey?
Okay, we have yeah, send us the email, send us your it's a web survey, so we send you a link for that, and then you fill it out. So there's a survey link, and if you email chromosome18 at utusca.edu, we can send you a survey invitation. So it's
But they
basically a
already
link.
have to be enrolled in the research study to be able to participate.
Right. That's a good point. Thanks.
That was going to be my next question. So thank you, Janine. Is that so basically you do need to be part of the research study. Okay, great. I know we've got a couple of other questions coming in. Is that, let me just quickly have a look here.
Yeah, I can find there.
So is that this is kind of like a kind of a favorite question that I know that kind of comes up occasionally, and it's like if Wicked kind of came to life today and they waved their magic wand and said you have an unlimited budget, what would you like to do, John? Kind of like as with that kind of with that unlimited budget.
Oh my gosh. I know we had talked about this. I mean, I think, you know, getting all of our medical records organized, that's a major factor, coding them all, um, and making them so that we could use them in a more analytical way for research, as well as a lot of sequencing. What we're doing for the Gabriella Miller cohort of 150, I'd love to be. Whoops, is my camera on? Oh, you know what? It turns off when I turn my screen sharing. But yeah, to be able to do some more deep sequencing on everybody to understand the effects of mosaicism, and understand which sequence variations are occurring near the breakpoints. I think doing deep sequencing would be amazing. And that's what we're kind of expanding with our partner, Santosh Gurura Rajan.
Awesome. Well, and I know that's kind of like a very hypothetical question, but hopefully one day that might be a real question. And this is kind of like from very quick couple of questions for me is that, and it kind of goes back to really, kind of your wish is that all the data being pulled is having to be done either by Brittany or by a physical task of doing it right, which is a huge kind of a huge task to do. Is that, can you give everybody kind of like an idea of what sort of time frame you've been putting the information in for like Gabriella Miller, for example? Is that like a week or a month or like 6 months or a year? I mean, what sort of time frame are we talking about here?
I think it takes like a month to do 150 participants. Oh no, actually, I take that back, to do one system. So if we're talking about probably like 10 major systems, like a system is endocrine, neurology, gastrointestinal, etc. Probably like a month for 100 participants per system. So years really to
Yeah,
do
okay. So it's just
a
to give kind
whole
of like
cohort.
everybody an idea of the amount of work that's being put into, to the information that's coming out. It's just
A
a
year.
huge
Yeah.
data input, which is being done manually at the moment, which you also mentioned a little bit about AI
Yeah.
and kind of how that's changing things. And is that going to be a bigger part of kind of the research moving forward, do you think? Or is it kind of, it's just not where it needs to be yet?
I think we're kind of on the cusp, and it's something we would apply. We're thinking about grants for applying for, because it is on the cusp of the possibility. Like before ChatGPT, I would have thought this was it had to be done by hand, which is very laborious. Brittany went through, I mean, not kidding, 100,000 pages of
Wow.
medical records, and not reading 100,000 pages, but sort of trying to
Like
identify the
shifting through them all.
major,
Yeah.
searching through 100,000.
Wow.
But something like ChatGPT or one of the other models, it's getting to be feasible that they can greatly accelerate it. It would be experimental at this point, but I think something like that would be very important in identifying patterns of disease going forward in the future. And our challenge is that we're getting medical records throughout the world that are sort of in different
In different
formats,
formats. Yeah.
from you know everything from like handwritten notes to scans, etc., and just kind of organizing that as a very labor intensive, sort of mentally laborious process that I think, yeah, AI can really accelerate in the future. But it is experimental, and
Right. Yeah,
we're
no,
definitely
it's down the
looking
road.
at that.
Just you brought it up in your presentation, and everybody's talking about how AI is going to change things. So just kind of trying to get an idea of what that might mean, kind of like, a few years down the road or what have you. But I know we're getting kind of a little bit short of time here. I think there was a mention about a sleep study. And
That's a great idea. I love that idea, actually. And I think that's something where, remote technology could be helpful, or yeah, potentially. And I think actually I could defer part of that to Dr. Karkar later in how to conduct that research, but that's a real issue with, I think, a lot of our participants, and understanding, how sleep's affected, in whom it's affected, and to what extent is really an important question.
awesome. Well, I know we got a few minutes that we're going to have a 5 minute break before Dr. Hale kind of comes on. Can I just thank you for a very exciting, for me, it was very exciting to see all the different items that you guys are getting into in a little bit more detail. And we're just going to be watching this space for kind of for more updates as they're happening. So thank you for joining us today and sharing all this wonderful information.
Thanks. Thank you, Neil. It's been a real privilege to work on this project with our participants and the research team. Thank you.
No, thank you. Okay, well, we're going to have about a 6 minute break.